All right, so now we're gonna look at equilibrium with acids, bases, and salts. So this is gonna bring us back to the last chapter where we were going over acids and bases. What I'd like you to take a moment and do is write the equation for this. All right, actually that's a good little review for us. So remember, products go on top, reactants go on the bottom. You're just gonna set it up. They didn't give us any numbers or anything, so we're just gonna put products over reactants. So take a second, do that. Okay, so let's set this up. So we know it's products over reactants. So our products are these two. So let's go H3O, H3O plus, CH3, COO minus, and then on the bottom we'll have CH3COOH. With this one, we know that water is amphoteric, right? So it can be an acid or it can be a base. So if we ignore water and we take a look at this problem here, we can see that this is an acid because it's donating its H that's over here. It's going to donate it over to the H2O and become H3O. All right, so now we're looking at Bronsted Lowry definition of an acid and base. And since these acid and base reactions take place in a beaker of water, we actually ignore all the water in these equations. Because if we don't ignore it, no matter what our numbers are for these three, this number is going to be huge. Because if you think about it, it's a beaker of water, most of it's water, right? And there's a little bit of acid in there, a little bit of base. So our K would always be really, really small because that number would be huge. So to only focus on what we care about, we actually ignore the water. And that's what it's talking about in here. So if we didn't ignore the water, the calculations wouldn't work, blah, blah, blah. And water, again, is our solvent. So again, we're going to ignore that. Now, when we ignore it and we're dealing with an acid, we actually call it Ka. All right, so now we have K, which was the one we started with, and now Ka is our new product constant for acids. All right, the equation looks the same though. All right, so we have Ka, it's called the acid ionization constant, and all we did was we ignored water. All right, but we still have products over reactants. Everything is still similar to what we've done before. All right, there's a Kb as well. So Kb is the base dissociation constant. It's the same as Ka, but for weak bases. Again, we don't use water. We're going to cut out water for any of that if we see it. All right, and then when do we not have equilibrium problems? All right, so this is kind of like, all right, what situations where do we not have equilibrium? So reactions that go to completion, meaning that they don't reach equilibrium and they're not reversible. So if you have something and it forms a gas, the gas floats away. So it can't form back and go backwards because it leaves the solution. All right, so when a gas forms from an aqueous solution, it leaves the solution and cannot be reversible. If you form a precipitate, when the precipitate forms, it's also no longer a part of that aqueous environment, so it can't be reversible. Or if you form water. So the formation of water makes a covalent molecule, which is not easily reversible. So these are when it doesn't work. And most of today is just setting the stage for being able to solve these kinds of problems. So we're just going over a whole bunch of rules, different things, introduction, and then we'll get into all the actual math shortly.